To witness it with your own eyes, you must rise at dawn, trek for half a day, scale a mountain, and then descend into its depths. Hidden within the rock strata lies a massive mechanical clock. Once every 1,000 years, it emits a unique chime through a cascade of musical pipes. This entire mechanism, synchronized to account for Earth's movements and celestial nuances, operates without a single volt of electricity. It runs on solar-heated graphite and the rhythm of a multi-tone titanium pendulum. This clock's designed to function for 10,000 years, even if no human ever returns. Its inventor, Danny Hillis, once a pioneer of high-speed computing, conceived what he calls the slowest computer ever built, intended not to compute faster, but to make civilization think slower, to expand our perception of time. Humanity has plenty of artifacts that direct our thoughts and imagination to the distant past, Stonehenge, the Great Pyramids, but we don't have something that turns our minds beyond the horizon of millennia ahead. So, when we speak of eternity, what do we imagine? What will remain of us? And for how long? Can we even grasp eternity? Or is our brain only capable of imagining extremely long but still finite stretches of time? You're now looking at what may be the longest time span ever calculated by a physicist in a scientific study. The question at hand was about the loss of information in black holes, and to solve it, the researcher had to estimate a specific turning point in the future, the Poincaré recurrence time, not the resurrection of the French mathematician, of course, but the moment the universe returns to a previous state. In principle, all the atoms that once clustered together at the dawn of time eventually spread out and filled the cosmos, but the universe is finite. There's no way to conjure new atoms from nothing, and so, inevitably, there comes a time when the scattered particles find themselves in the same configuration once again. How long would that take? Forever? Surprisingly, no. In one cosmological model, a finite, albeit unimaginably large, time was calculated, and in the model corresponding to our universe, the Poincaré recurrence actually happens sooner than you'd think, because there's only a limited number of quantum states it can occupy. So maybe we're not even close to brushing up against true eternity. What if, instead, it could be calculated? Would we need a number larger than the number of atoms in the universe? That question leads us to a deceptively simple game. The game of trees. You begin with colored circles, seeds, and connect them with lines, branches, to form trees. The rules are strict. The first tree can only have one seed, the second no more than two, and so on. But the game ends the moment you create a tree that replicates any structure you've already built. In essence, you're forbidden from repeating any combination of circles and lines. Paul Erdos, a famously eccentric mathematician who referred to children as epsilons, the mathematical symbol for something infinitesimally small, was known for arriving unannounced, sleeping in your bed, and always bringing an intriguing math problem. One day, he posed a question to a colleague. Could the game of trees go on forever? More than 50 years later, a mathematician finally proved in his dissertation that the game cannot continue infinitely. But then, how long can it last? That depends on how many types of seeds you use. With only one type, you can build just one tree. With two types, you max out at 3, but introduce a third seed, and the system explodes. The number of possible trees becomes so massive, it can't even be fully written out. The total is known to mathematicians, but the number is so large, it exceeds the data capacity of the universe. To put that into perspective, if you've heard of Graham's number, once considered one of the largest numbers ever used in a serious proof, this game's number dwarfs it. Graham's number is a speck by comparison. Let's play a little thought experiment. Suppose we draw one tree per tick of Planck time, 10 to the minus 44th power of seconds, the smallest interval of time that physics still considers meaningful. To give you an idea of how small that is, more Planck times fit into a single second than the number of seconds that have passed since the Big Bang. And yet, we press on. One tree every Planck tick. After 1 year, we generated more than a trillion trees.
Over a trillion 200 billion.
But this is only the beginning. We play for a lifetime, and when we're gone, AI descendants, digital replicas of our minds, carry on the game. 300 million years pass. Continents merge. The sun burns brighter. Still, the AI persists. 600 million years. The Earth's carbon cycle collapses. Oxygen plummets. Plants vanish. 800 million years. All complex life is extinct, but two robotic stoics keep building trees. Billions of years pass. The Milky Way collides with Andromeda. The sun becomes a red giant. Earth is swallowed, and the AIs evacuate. In a quadrillion years, the sun is a distant memory, and yet the game goes on. Between 10 to the 40th power and a Google years, black holes dominate. Eventually, they evaporate, leaving behind only a dark, cold universe filled with stray photons. The AIs persist, but at 10 times 10 to the 122nd power of years, we arrive at the Poincaré recurrence. The universe, which can only exist in a finite number of quantum states, resets. It returns to its starting conditions, erasing everything, including the unfinished game, unless the players existed outside of time, where counting becomes meaningless. Because while the number of tree moves is unimaginably large, it is still finite, and provably so. But what if the cycle repeats? If the universe evolves, collapses, and evolves again, over and over, then perhaps this is what infinity truly looks like. Not a line, but a circle. Interestingly, recent data have lent new credibility to a once-dismissed theory, cyclic cosmology. According to it, black holes could survive between cycles, albeit in transformed states. From the very beginning of expansion, these ancient remnants, what physicist Yakov Zeldovich called cosmological veterans, might see the birth of galaxies, structures far too mature to belong so close to the Big Bang. So what do we see in the latest images from the most powerful telescope in history, the James Webb Space Telescope? Quite possibly exactly what was long considered unlikely. The early universe appears to already host many massive, modern-type galaxies. These findings challenge the long-held assumptions based on Hubble's data, which had implied a drop-off in the percentage of spiral and spherical galaxies with distance. Hubble simply couldn't resolve shapes at that scale, but Webb can. Now we're seeing galaxies that shouldn't yet exist, at least not by the timelines we thought we understood. But while we're still deciphering cosmic infancy, let's zoom out. Let's shift away from thinking about eternity as a ridiculous amount of time. What if eternity isn't about duration at all? What if it's about the absence of time? To even think about eternity, we may need to unthink time itself. And believe it or not, physicists may have already done that, experimentally. They used a long-forgotten paradox, one that mathematicians had solved ages ago but which seemed irrelevant to the physical world, until now. Picture this: you kick a ball, look away and look back. The ball is somewhere else and no longer moving. Clearly, motion happened, even though you didn't see it. Now let's try to observe that motion directly, as closely and continuously as possible. But there's a problem. The closer you look, the more time seems to disappear. At every single moment, the ball is in a fixed position. It's never between 2 points, not even for a fraction of a second. There is no moment where motion is caught in the act. It turns out the ball is always at rest. Movement then becomes a kind of illusion, a perceptual flaw. Just like how digital screens trick us into seeing fluid animation instead of static pixels, our brains, like our eyes, might lack the resolution to detect the truth. What if time works the same way? This isn't just about faulty perception. This might be baked into reality itself. Eternity might be hidden in the very fabric of the cosmos, and our minds are just too low-res to see it. Because if this eternity is real, it doesn't just mean that time doesn't exist. It means that everything exists at once. All events in the universe don't occur in sequence. They are simply there. You closing YouTube, you being born, dinosaurs roaming Earth, the heat death of the universe. Not past, not future, not present, just always. So why don't we see it? Maybe because we, like that ball, are forever stuck in a single point, one moment, unable to step outside it. We can't walk the aisles of time like rows in a library and peer across the timeline. We are bound to our dot, bound to experience life as a trickle, never as the flood it really is. And yet, physics says this kind of eternity may be real. Worse or better, it falls straight out of the most well-supported theory we have about how the universe works. In this experiment, the ball was replaced with something even stranger, an unstable quantum system, specifically a group of cooled sodium atoms trapped in a standing wave of light, essentially a series of tiny energy wells. These atoms couldn't simply jump out. They didn't have enough energy, and there was nowhere to get it from. But quantum mechanics has a trick: quantum tunneling. This is where particles don't climb out of a trap. They just disappear from one place and reappear in another, as if by magic. So these atoms don't break out of the wave, they just tunnel from one pit to the next. But if they spread out into different pits, the original system decays. Over time, the whole system dissolves as the atoms scatter and become unrecognizable. Why does this decay happen? Because in the quantum world, nothing can stay in the same state forever. At any given moment, a particle might be in one place, or it might not. Just like Schrödinger's cat, both alive and dead, until someone opens the box, until a measurement is made. And that's the twist. Measurement freezes reality. The moment you observe the particle, it stops being a cloud of probabilities and becomes something definite. That act, just looking, holds the system in place. So, what happens if we never stop looking? What if we keep measuring, over and over, constantly, without pause, not once in a while, not occasionally, but continuously? Then Schrödinger's cat would never die. The particle would never move. The system would be frozen in place. In other words, time would stop. This isn't a metaphor. In the actual experiment, the decay didn't halt entirely, but it slowed dramatically, not because of some limitation in physics, not because the rules broke, but simply because the measurement wasn't happening fast enough. They were only measuring every microsecond, 1/1,000,000th of a second. To you and me, that's nearly nothing, but to a quantum particle, it's an eternity. Physicists jokingly call this quantum theater, using precision lasers to freeze electrons in ultra-slow motion. Today's advanced tech lets them slice time into attoseconds, a billionth of a second. To put that in perspective, if the Flash ran at the speed of light, in a microsecond he'd cover about 300 meters, and in an attosecond no more than the size of a single hydrogen atom. And the most stunning part? This limit to our ability to go deeper into the fabric of time is only technically, and therefore essentially, temporary. What if we could reach the so-called elementary particle of time itself? Not literally, but conceptually. What lies beyond the edge, where physicists no longer speak in seconds or microseconds, but confront the absolute limit of our understanding of time and space, Planck time? Could time itself be made up of indivisible units? Quanta of time, with no instant between them? This idea, known in physics as discrete time, suggests that the universe might not flow smoothly, but instead jump from one moment to the next, skipping all in-between states. Like frames in a film reel flashing by so fast we can't perceive the gaps. Discrete time sometimes appears in the speculative work of physicists probing quantum gravity, but the concept runs into a major obstacle: our own minds. Because when we imagine this, our brains instinctively follow time's arrow. You're probably doing it right now, mentally lining up moments from left to right or from past to future, one step then another. That's the causal structure of reality, where each moment exists because the previous one caused it. It's how we think, how we live, how we make sense of anything. So if the universe really is organized like this, each event following from a previous cause, then, in theory, we can trace this line backward. From this very breath you're taking, to the formation of Earth, to the birth of stars, to the Big Bang itself. But wait, what caused the Big Bang? Why does the timeline stop there? Why can't we go one step further? Because if we try, we fall. right into a black hole of logic, down the rabbit hole where math breaks, laws collapse, and everything stops making sense. We reach the edge of our formulas and find the singularity, a point so extreme, so compressed, that our understanding of nature just gives up. And here's the irony. The deeper we try to comprehend eternity, the faster it escapes us. The closer we get, the less we understand, like chasing the horizon. But here's the most maddening part. Modern science, which rejects infinity as a real number, still places eternity at the heart of its models. We killed infinity and then made eternity one of the pillars of our understanding of the cosmos. Isn't that insane? Let's rewind to one rainy October day where on the side of a muddy road a strange man was found unconscious. In that dismal weather, even the few indifferent passers-by couldn't ignore the sight. The man lay motionless, mumbling incoherently. When someone finally turned him over, the onlookers recoiled in horror. It was Edgar Allan Poe, the renowned author of dark and enigmatic tales. A man who had vanished just days earlier without warning, apparently healthy. And now he was disoriented, dressed in ill-fitting clothes, muttering a single word over and over. Reynolds. No one close to him knew anyone by that name. Even today, scholars remain baffled. He was taken to a hospital where his condition deteriorated. Just before his heart gave out, Poe uttered one final, cryptic line. Who erected the firmament and sustains the universe, has inscribed his laws clearly on the foreheads of every man and on demons incarnate. A moment of madness, a fevered hallucination? Possibly. He was grief-stricken, having recently lost someone dear. But there was more to Poe's unraveling than tragedy. Just before his death, he had published a deeply uncharacteristic work, not a story but a book on astronomy. In it, he gathered the latest scientific findings and dared to make a radical claim. The universe is not eternal. It is finite in time, capable of changing, and may even give rise to other universes beyond our interaction or perception. At the time, such an idea was sheer heresy. Poe was dismissed, his ideas deemed the feverish ramblings of a deranged man. But over a century later, the physics world caught up. The end of the 20th century brought the theoretical frameworks, calculations, and observational data needed to confirm that Poe, poet, outsider, and visionary, had been right. What once seemed incoherent became a revelation. In Poe's time, science believed the universe to be infinite, uniform, and unchanging, a celestial clockwork, ticking endlessly in both directions. If we know where the moon is now, we can say with accuracy where it was 1 billion years ago and where it will be in the future 1 billion years from now. The universe, to the point of gnashing teeth, is like a perpetual clock in which, without beginning or end, everything runs smoothly and predictably. But that would mean that at any point in the sky, sooner or later, there would be a star at some distance from us, which would mean that the sky would be flooded with infinite light, which is not the case. It doesn't, of course. And it was Poe, not an academic, who first offered a compelling explanation. What we now call Olber's paradox was addressed by a writer of macabre fiction. In his radical Cosmology, Poe described a finite, dynamic universe, always in motion, always evolving, and for that, his book was soon banned in the United States. Poe argued not just that things within the universe change, a notion everyone accepts, but that the universe itself changes. Space and time are not eternal fixtures. They too had a beginning. In his writing, Poe proposed that the universe began as a unified point where matter and energy were one. He was echoing, far ahead of his time, ideas that would later be formalized by Einstein's relativity and further developed by Georges Lemaitre, the Catholic priest and mathematician who coined the concept of the primordial atom, the earliest version of what we now call the Big Bang. This was radical. It meant that space-time itself had a beginning. But Poe didn't stop there. He claimed that before the beginning there must have been something eternal. For Poe, that was God. In today's scientific language, we call that boundary the singularity, a point at which all known laws of physics collapse. At that moment, our equations stop working, and our understanding of cause and effect begins to dissolve. The question, what came before the Big Bang, suddenly loses all meaning. Poe, without access to quantum mechanics or entropy, managed to portray a universe that was finite, dynamic, and unpredictable, a remarkably close reflection of today's cosmological views. Of course, he got many details wrong and couldn't envision a universe without time itself, as some modern physicists now do. As physicist Sean Carroll puts it, time, the thing that is so important to us every day in ordinary life, disappears the deeper we delve into the laws of nature. Even Einstein noted that past, present, and future are only an illusion, though a very persistent one. According to the special theory of relativity, one of the most tested and confirmed theories in science, time is not absolute. The same event can occur at different times for different observers. For example, the starlight you see now may be from a star that no longer exists, and yet to you, it's still there. We can't even say with certainty what's happening on Mars right now. It's 20 light minutes away. What we see is always 20 minutes old, and nothing, not light, not information, can reach us faster than that. So even in everyday interactions, we are always trapped in the past. We live in isolated points in space-time, only thinking we move through time because our brains assemble the illusion of continuity. Everything else, every object, event, person, is also stuck in its own moment. Even the apple in front of you is already in the past, seen with a delay processed by your brain just slightly after it happens. This leads to an astonishing consequence. Past, present, and future don't actually exist as separate categories. All events exist simultaneously in what's called space-time, a fixed, four-dimensional structure. Movement itself requires change in both space and time, so unless we're gods capable of escaping the universe, we cannot move outside time. This idea is known as eternalism, from the Latin aeternitas, eternity. According to eternalism, the universe is a single, unchanging block, with all events already encoded in it. Yet not everyone agrees. Some critics, especially philosophers, but also a few physicists, challenge this view. One of them is Lee Smolin, who wrote Time Reborn. He argues that if we accept this frozen, timeless universe, we must also believe the laws of physics were always exactly as they are now. That robs us of the ability to understand how or why our universe came to be this way. Worse still, it might contradict quantum mechanics, where observation plays a crucial role in determining outcomes. In a block universe, where everything is fixed, there's no room for a genuine observer, and no room for the unknown. You know, while working on this material, I kept circling back to one unsettling thought. What does all of this mean for how we understand our lives? Because even if time is an illusion, it still feels real to us. We live by it. Our entire civilization is built on the assumption that time flows, that events happen in sequence, that decisions matter. But what if, in truth, we're just living inside a movie that's already been filmed? And even when we think we're making spontaneous, rebellious decisions, breaking the script, we're actually just playing out our part in a larger, already written story. Is the act of rebellion itself just another scene in the universal script? Poor Poe. And for those of us who lean, consciously or not, toward mystical thinking, not necessarily belief but a kind of irrational feeling, this all begins to sound a lot like eternity, like a secular version of immortality. Maybe all those we've lost are not truly gone, like the actors in old films who are no longer alive but whose performances we still watch. They exist, in a sense, because we remember, because we look, and maybe, just maybe, so will we. Not because we've been canonized in cinema or immortalized in videos, but because we are part of the movie of reality itself. And once you're in the film, you're in it forever. Of course, that's a dangerous slope. Not science, but a poetic mirage that feels like religion. It's tempting to blur the line, but the resemblance only exists because scientists and storytellers like me use metaphors to talk about math, physics, and truths too strange for ordinary language. Still, the more I explore science, the more I realize that our understanding doesn't only run on reason. Our minds are fueled by more than logic, and that's okay. There's nothing dangerous about dreaming, so long as we don't confuse dreams with reality. But sometimes, just sometimes, it's worth pausing and asking, what if? If you enjoyed the video, hit subscribe and ring the bell. Thanks for watching. See you in the next one.